So the today topic is directive influence of electron releasing groups and electron withdrawing groups on benzene ring. If the benzene ring is mono or disubstituted. Okay, so this is an important topic to know the orientation of incoming group on benzene ring. So let's say, for example, if you have a benzene ring, suppose if you don't have any substitution, then you can say all the 6 carbons are equal. Whenever you don't have any substitution on benzene ring, all the 6 carbons are equal. All the 6 carbons are equal. Suppose if your benzene is mono-substituted or disubstituted, if your benzene is mono-substituted or disubstituted, then the position of next incoming group is decided by the groups which are already present on benzene ring. Okay. So whenever you are discussing about this, you have to know about two types of groups will be there. So one is electron donating group and another one is electron withdrawing group. So the electron releasing groups or electron donating groups both are same. So we can say this is electron releasing groups. So these group will show plus I and plus M effect. For example, like CH3, C2H5. So this will show plus I and OH, OCH3 and NH2. So these groups will show plus M effect. Okay, and electron withdrawing groups, they will show minus I effect and minus M effect. So the examples of minus I, you can say halogens. The halogen shows minus I and like NO2, CHO, COOH, they will show minus M effect. Okay, but here we have an exception. Even the halogens are showing minus I effect. They act as activating groups. That is, they orient the next incoming groups at the ortho and para position. So this exception is because of what? So the exception is because of due to presence of lone pair of electrons on halogen. Understood? So let's see how this will be shows directive influence on next incoming group. See, for example, I'm taking a benzene ring which consists of an electron releasing group. So whenever I have an electron releasing group, the next incoming group will be at the ortho position or para position. Okay, so this you can explain based on a mesomeric effect. You can explain based on mesomeric effect. Let's say, for example, if I have CH3, so which is plus I and plus H group, this CH3 reacts with Cl2 in presence of anhydrous AlCl3. So this is what? So this is our Friedel-Crafts, chlorination. So the substitution will be takes place, that is electrophilic substitution will be takes place at ortho position and para position. Okay, so whenever you have a single group. So similarly, for example, if you have OH, which is shows plus M effect, okay, this will undergo nitration in presence of HNO3 and H2SO4. So the orientation will be takes place OHNO2, that is ortho position, and OHNO2, which is at the para position. So that means with respect to OH, the substitution is at ortho position. With respect to OH, the substitution is at the para position. Whenever you have single substitution, we can discuss like this, or we can find the next position of next incoming group like this. For example, if we have two substitutions, both are electron donating, that is both are activating. So CH3, so this will show what? Plus I, and OH, so this will show plus M. So now I have both are activating groups. So in this situation, the position of next incoming group is decided by the group which is strong. So if you compare the plus I and plus M is dominating over plus I. So the next incoming group will orient ortho to OH or para to OH. Okay, so because of this is a strong one like this. So whenever you have two electron donating groups, the things will be happen like this. For example, if the same thing undergoing chlorination in presence of AlCl3, so the product will be with respect to OH, ortho and para. So this is at ortho position and para position. Understood? Okay, so this is the case of if you have only electron releasing group. Suppose if you have one electron releasing group, so whenever you have electron releasing group, from these examples we are clear that if you have electron releasing groups, the next incoming group will be added at the or substituted at the ortho position or para position. Okay, so let's say an example CH3NO2. Okay, so this is plus I and this is minus I. Now, with respect to electron releasing group, the substitution should be takes place at the para position and ortho position. So this is the para position and this is the ortho position and this is para position with respect to CH3. But this is meta position with respect to NO2 and this is also meta position with respect to NO2. So whenever you have one electron donating group and electron withdrawing group, then the substitution takes place with respect to electron donating groups, ortho and para. With respect to electron withdrawing groups, it will be at the meta. Understood? Now, the thing is, suppose if you have two electron withdrawing groups or one electron withdrawing group, say for example, suppose I have nitrobenzene. Again, this nitrobenzene undergoes nitration with HNO3 and concentrated H2SO4. The substitution will be takes place at meta position. As this is electron withdrawing group, the substitution will be takes place at the meta position. Okay. Suppose if you want to do further at high temperatures, HNO3 and H2SO4. So compared to this one, this is less reactive because of two electron withdrawing groups. So the thing is will be like this: NO2, NO2, NO2. So everyone is mattered with each other. For example, if I have CHO group, which is an example of electron withdrawing groups. Okay, suppose if you do the nitration, so the substitution will be takes place meta to CHO like this. So here the things what you have to remember is, suppose if it is electron relation group, the groups will be at the ortho and para. If it is electron withdrawing groups, the substitution is at the meta position. Hope you understand this concept, and this concept is useful for both JEE and NEET students. So myself, Vishwanath, a chemistry mentor. If you like the concept, share the video and subscribe the channel. Okay, thank you.